Hello everyone, this is Mrs. Lindsay. Today we're going to talk about limits, including vertical and horizontal asymptotes. Okay, so let's first take a look at an example. Our example that we're going to look at is the function f of x equals 2x plus 2. We're going to take a look at the numerical approach here by looking at our table with a set of data that satisfies this function. I want you to pause this video, write down what you observe as you take a look, and again consider the values of x approaching 1 from the left. So as it's getting closer to 1, what do you observe? Okay, so hopefully you observe that it is, as it's getting closer and closer to 1, it's getting closer and closer to 4. And this actually isn't 4, this is a rounding error in the calculator, but it is approaching the value of 4. So in our limit notation, we would write this as the limit as x approaches 1 from the left side, f of x equals 4. Okay, so now let's switch on over and take a look from the right hand side. And I would like you to go ahead and pause, take a look at your calculator on this, plug it in. Pause the video if you need to find your calculator, plug that in and look at your table. And then again talk and write down some observations as you see it approaching from the right hand side. Okay, so if you plug this in your calculator and then again you look at the values, and you can also look at the graphs. But if you look at the values on your table again from the right hand side, so as it's approaching 1, again it's still getting closer and closer to 4. So this limit notation here would now be as x is approaching 1 from the positive, the right hand side, the limit is 4. Okay. So again, if you actually already looked at the graph of that, it should look like this. So again, what is happening as it's approaching 1? So here's our value of 1. What is it happening? What's it doing as it's approaching from both sides? What is our limit going to be? And hopefully again you see that it's getting closer and closer to this height of 4. That is the definition of our limit. So again, it's getting closer to 4. So we use this limit notation. We would say limit as x approaches 1 of f of x equals 4. And again, a special little note here. Please notice from the right and the left hand side, we figured out that it's approaching 4 from both of those, so they are equal to each other. Okay. So taking a look at our next graph here, describe what happens to g of x coming towards x from the left, so in this case from the left, and then when it's coming from, I'll do this one in red, from the right side. So if you notice that coming from the right side, it has a height of 4. But if you're coming from the left side, it has a height of 2. So in other words, there is no limit when it, at x equals 1 because the left and the right hand side limits don't match. So we use LHL to talk about the left hand limit would not equal the right hand limit, which is RHL. So left hand limit doesn't equal the right hand limit, which would then mean the limit as x approaches 1 does not exist. So in other words, the limit as x approaches 1 of our function g of x does not exist. So what is our actual formal definition of a limit? So go ahead and take a minute, write this down, and then think about how you would actually describe it in your own words and write that down as well. So go ahead and pause this and do those two things, please. Okay, so again, the formal definition, if f of x becomes arbitrarily close to a unique number L, as x approaches the number c from both sides, then the limit of f of x approaches c is L. So again, that can be a little bit wordy, so I kind of put my own thoughts down. What is the y value approaching at a given x value? And then the notation is the limit as x approaches c of the function equals L, which is the limit. So again, a little bit of definition there. Okay. But we actually have to think about when doesn't exist. And we kind of talked about that in the first couple examples. So the limit, when does it not exist? There are 3 cases here. when the limit doesn't exist. One we talked about, again, the left and the right hand limits have to be equal. So if they're not equal, it doesn't exist. If f of x increases without bound, or if f of x oscillates between two fixed values. So in this case here, let me go ahead and just give you a little example. So if I did something like f of x equals 1 over x, that graph looks like this. So if I'm finding the limit at that value of x is 0, it's increasing to infinity or negative infinity, so it's going without bound. So again, that's where the limit would not exist. And another example here of where it would be oscillating. So the limit here, as x approaches 0, cosine of 1 over x. If you were to graph this, it literally is looking something like, and then this just shoots up and down, almost kind of like our heart rate monitor. So it's oscillating up and down really, really quickly around that value there. Okay, and I can go ahead and plug that in and show you that graph. Okay, so here's the graph. As you can see, I actually zoomed in just a little bit. You can see though, if I even zoom in a little bit more, this is just going up and down, or in other words, oscillating between those values. So when you have that case, again, there is no limit. So let's go ahead and try some examples here graphically. The first one here, we're going to take the limit as x goes to 0. So as x is going to 0 from both the right and the left hand side, it is at a height of 1. Next one, as it's going to 1, again from the left side and the right side, if you notice, these have two different heights, so this one does not exist. In this case, now we want to take at 1 and take it from the left-hand side, so the limit as it's going from the left-hand side, that has a height or a y value of 2. And if I look at 2 here, again from the left-hand side it's approaching 2, so I'm going over here as I get closer and closer to 2. This is going to negative infinity. Technically, this does not exist because, again, a limit cannot increase without bound. However, if you put negative infinity, I would also accept that. But technically, the correct answer should be does not exist. Okay. I'd like you to go ahead and take a look at this next example. Fill in your answers for that, and when you're ready to check your answers, go ahead and push play. Okay, so the limit as it approaches -1 has a height of 4. The limit as it goes to -4, again, the left and the right hand bounds are not the same, so they are not, it does not exist. The same is true for as the limit approaches 2. Left and right hand limits are not the same. And now as it goes to infinity, again it's going without bound, so I would take either negative infinity or it does not exist for that one. Alright, so what do we do if we can't take a look at the graph? So algebraically, what are some things that we can do? Go ahead, take a minute, and please write these down, take a look at them, and read them. And I can tell you right now, direct substitution is definitely the first option that we're going to do there. But take a minute, read these, write them down, and we will go from there. Okay, so we've actually already talked about graphically and numerically in the first couple examples. We are going to now do direct substitution. This is always what I would do first. Every single time I would do direct substitution. So in other words, that literally means just plug in that value. And a couple little reminders here before we get going. If you get the form 0 over 0, this is what we call the indeterminate form. This is when you just want to just keep going. You've got to use some of your algebra, tools of algebra to help you. So in other words, you might want to factor and see if anything cancels. You might want to multiply by the conjugate. You might also just need to simplify complex fractions. Okay. Those are just a few ideas, and we'll get into some of these as we go along. Okay, so again, if you can't cancel, a couple of things, then you have a removable discontinuity, so in other words, a hole. And then if you have a number over 0, it's undefined and is a signal of a vertical asymptote. So we'll get into those as well. All right, so find the limit if it exists. So use direct substitution. I'll do A first, and then you guys can do B. First thing that you want to do is try direct substitution. So literally, I'm just going to plug in 3 for the x, and I get that to be 12. That is my limit. Okay. So go ahead and try to do B and so see what you get with that one. Okay, so hopefully you realize when you plug in 1 in there, you get 0 over 0, which is what we call the indeterminate form. So we got to keep going with this thing. We got to try some of our algebra tools to help us with this. So hopefully you recognize that the denominator is a dots problem, and I can factor that into x minus 1, x plus 1. Then the benefit of that is I can simplify it. I can cancel the x minus 1s. And now I want to go right back to direct substitution. So if I plug 1 in for x, I get 1 over 1 plus 1. So here my limit would be a half. Again, direct substitution first. If you get your indeterminate form, try some of your, again, algebra ideas there to see what you can come up with. So let's try C. In this case here, again, if you plug in 0, I'm going to get 0 in the numerator. And if I plug in 0 here, I get 5 minus 5. So again, I'm getting my indeterminate form, so I got to keep going. So what are some of the things that I can do with this? Well, since I have a radical, we can actually multiply by the conjugate. And the conjugate is taking whatever that radical is, where it's actually a binomial, and I'm going to change the sign. So I'm going to multiply that on the top and the bottom. So I'm going to distribute through the x in top. So I get x square root of x plus 25 plus 5x. And then the denominator, hopefully you realize that the purpose of multiplying this, when I multiply the first radical, it just simply becomes a radical would then cancel out, just become x plus 25. And then I'm going to get minus 5 square root of this plus 5 square root of that. So every single time, I'll just kind of write it like this. Every single time, those middle terms will cancel each other out. That is the point of multiply by the conjugate. So I'm really only having to multiply the first terms and then the last terms there, which is minus 25. So some people skip that middle step, and that's fine if you would like to do that. So again, I'm going to just simplify here just a little bit. And in this case, I'll have x in the denominator because 25 minus 25 is 0. And what I kind of recognize here is maybe I shouldn't have distributed so quickly. So maybe if I just take that x back out, you can see here that then cancels. And then we have the limit as x approaches 0, square root of x plus 25 plus 5. And now I can do direct substitution, plugging 0 in there, and I would get square root of 25 plus 5, which would give me 10. We're going to skip D for now. We will eventually come back to that. I want to move on to the next page here. And with these rules, I know there's a lot of rules here, but this is really much more common sense because it's showing you that the limits hold true for scalar multiplication as well as sum or difference, product, and quotient. So I don't want you to get too hung up on these. I'm sorry, and even the power rule. We're just going to jump into a couple of more problems here with limits of infinity. But before we do that, we need to review vertical and horizontal asymptotes. So I'm going to go ahead and stop this now, and we'll finish with the second part of 1.5 and 1.3 video continued, which won't just be a couple more minutes. So if you could pause this or stop this and then continue to watch the other one.